Alrighty. So today we are going to talk about evolutionary game theory. That is the last, so I'd say 2 lectures ago, or maybe, 2 lectures ago, we did a sort of intro to regular game theory, that is the way economists do game theory. And then today we're going to talk about the way evolutionary biologists do game theory and how those things relate. And so in what we talked about a couple of classes ago, we were talking about choices getting made, and what makes choices is an agent, or a person, I guess, really, or an organism, whatever, but it's an individual agent. And you can think about things about, rational prospective reasoning and what that would lead agents to decide to do and how social preferences would change that and so on. But when we switch to the question of evolutionary game theory, we have to think about what evolves. And what evolves is not individuals, but what evolves is populations. That is to say, the definition of what evolution is it's a change over time, not of an individual, but of a population. It's the change in the frequency of genes, or in our sort of game theoretic context, strategies in a population over time. And it proceeds at the pace of generations, be they actual genetic reproduction generations or just learning. But the point is, when we're thinking about things evolving, we're thinking about how the population is changing over time. And the Nash equilibrium concept that we have talked a lot about is a static concept. That is to say, we just do some calculation and we say, well, okay, something is in equilibrium or it's not in equilibrium. And what we conclude from that is that if something is in equilibrium, that means neither person has an incentive to unilaterally deviate, and therefore we expect things not to change. So the equilibrium, the Nash calculation, is a calculation that tells you something about lack of change, or and it's inherently a static concept. And when there's only one Nash, then it doesn't matter what the dynamics are or how things change over time. It's very clear that the theory is predicting that everyone should wind up playing that Nash, no matter what the initial what the initial conditions are. That is, no matter what the initial frequency of strategies within the population are. If there's only one Nash equilibrium, eventually everyone should wind up playing the Nash equilibrium. And so you could say, I don't really care about the dynamics, that is how things actually specifically are changing over time, because I know that in the long run, we're always going to wind up at everyone playing the Nash. So the dynamics are not my problem. But when there's more than one Nash, or when no strategy is a sort of symmetric pure Nash equilibrium, then the dynamics matter, because the question would be, what do you expect the population to happen? What do you expect evolution to lead to? And the answer is ambiguous. And you need to note something about the current state of the population. So you want to say, where is the population starting? And then where is it going to evolve to from there? And in the case of multiple equilibria, the question is, which equilibrium do you expect to wind up in based on your current position? And in the case of no equilibria, the question is, what do you expect to happen? And so there are different ways that you could try to answer these questions. The way that economists traditionally have tried to answer these questions, in particular when there's multiple equilibria, they start adding extra criteria to say, well, these are called refinements on Nash equilibria. They say, well, okay, in order for something to happen, we expect if the equilibrium, people will play the equilibrium that's more efficient. Or people will play the equilibrium that have some extra features or whatever, and so they do these different sort of adding on extra conditions in order to get down to the point where there's only one equilibrium left, and then they say, okay, this is the one that I expect to happen. But those sort of additional criteria are just kind of subjective things that people make up and say, well, I think this kind of makes some sense. And so the approach of evolutionary game theory is to answer this question in a different way, which is from the principle of natural selection and saying, assuming that natural selection is happening, how do you expect the population to evolve? And so economists actually got into evolution in the 90s because it presented a way of solving this problem of which equilibria are you going to wind up in. That's just historical side. Okay, so what this means is, as I think you guys probably know, natural selection is the idea of the survival of the fittest. And what survival of the fittest means is it's a statement about how the frequencies in the population change over time. And so if you imagine that you have a population where fraction p of the population is using strategy 1 and the remaining 1 minus p is using strategy 2, the question that you then have is, when an offspring is produced, like how are these frequencies going to change? And another way of saying that is that offspring going to be of type strategy 1, in which case P is going to increase because strategy 1 is going to become relatively more common, or is it going to be an offspring of strategy 2, in which case P is going to decrease because the frequency of strategy 2 is going to increase. And so the key question then is, when the offspring is produced, is it more likely to be a type strategy 1 or type strategy 2? And the fundamental principle that drives evolutionary game theory is the idea that a strategy that leads to one offspring being produced is going to fundamentally do less well and be outcompeted by a strategy that causes 2 offspring to be produced, for example. And more generally, when we talk about evolutionary game theory, the payoffs are the sort of numbers of offspring produced or the probability of offspring being produced, such that if the payoff in the game of strategy 2 is higher, then it's more likely that any given offspring that is produced is of type 1, and P will tend to increase. If the payoff of strategy 2 is higher, then strategy 2 is more likely to produce offspring, and P tends to decrease. And so what that means is that the overall change in P is going to depend on the relative payoffs of the 2 different strategies. And specifically, as I sort of just said on the last slide without actually writing it out, so we're going to pi as payoff. So this is the payoff of strategy 1. If the payoff of strategy 1 is greater than the payoff of strategy 2, S1 is more likely to reproduce. That means S1 becomes more frequent, which means P increases. And conversely, and so then the key point about evolutionary game theory, as opposed to just evolution in general. So, as we talked about at the beginning, if you have traits like being faster or stronger or, not dying as much or whatever, these are things that are more or less universally good. And so that just, agents with these strategies will have higher fitness and so will tend to, increase in the population regardless of, is that like in?
This phone.
That ain't right. Hello? This is the wrong number, sorry. All right. Without further ado, it's so weird. Like, what is that doing here? Oh, it's for me to call them, I think, if I need classroom support.
Yeah.
Well, hopefully you guys haven't gotten out of control yet, so haven't you had to use the phone? We had calling backup, I think. Okay, so anyways, in traditional evolution, if one thing has a mutant has a higher payoff, it just spreads. But the point of evolutionary game theory is that the game part is we have social interaction, and so your payoff depends on what everybody else is doing. And so that means that as P changes, the payoffs also change. Because now the makeup of the population is different, who you're playing the games with is different, and so the payoffs change. And conversely, in the case where the payoff of strategy 2 is higher than strategy 1, then P tends to decrease. And so this gives you some way of determining the dynamics. You can know at any given makeup of the population, how are things going to be changing by looking at the payoffs. And the key idea here now of what equilibrium means is that the two payoffs are equal. If the two payoffs are equal, then you don't expect anything to change because neither strategy is doing better than the other. And so this balance creates a sort of equilibrium state in the population. Now, that's one way that you can have equilibrium. And in that mixture, that's sort of both strategies are there in the population. They're both doing equally well, fine. But there's another possibility, which is at the two extremes. So at p equals 0, where it's all strategy 2, or p equals 1, where it's all strategy 1, there's no variation in the population. All of the agents have the same strategy, and therefore there's no way that anything can change because all of the offspring that are being produced are of one type. And so this is another kind of equilibrium. But, you know, there is actually, as you may recall, when we sort of in the intro lecture talked about what evolution is, we're saying that one of the key features of evolution is mutation. And this is why our mutation becomes really important, or one place that mutation is really important, which is when you have a population where everyone in the population is playing the same strategy, then mutation can occur, which is to say when an agent has an offspring, the offspring is not a copy of itself, but instead it's, it's somehow different. It could be picked at random, it could be a small modification from the parent, whatever, but that introduces variation back into the population. And so if you're in an equilibrium and a mutation occurs, then by definition that means the mutation is going to move the population out of the equilibrium because, now things have changed. And so the key question for wanting to know about is something evolutionarily stable, is something a situation that you expect to actually occur in the world, is that when a mutation arises such that the population gets shifted out of the equilibrium, does natural selection move the population back to the equilibrium, in which case it's sort of evolutionarily stable, or once you get pushed out by an equilibrium, does natural selection carry you or carry the population away in some other direction? And so to sort of walk through that logic, say in the case of a stable equilibrium, then after the mutant arises, it doesn't, it returns to the equilibrium. And so what that means is that, okay, mutation by definition is going to increase the frequency of one strategy and decrease the frequency of the other strategy. And so in the case that this equilibrium is stable, this new mutant, this new sort of, when you sort of shifted the population to make one type more common, if that new mutant has a lower payoff than the strategy that was not the mutant, you could call it the resident, then that means that that new mutant will die out because it's not doing as well as the other, and things will move back to where they were before the mutant arose. And what you see is that is sort of that question of, okay, when a mutant arises, does the mutant have a higher payoff than what was there before, in which case he'll get a foothold, or does it have a lower payoff, in which case he dies out, is actually exactly analogous to the Nash condition of if you know that the other person is going to play the resident strategy, in this case X, can you improve your payoff by switching to some other strategy? And so this is the sort of link between the Nash criteria and the evolutionary stability criteria. And again, this evolutionary stability is this key concept of whether the population will stay where it is despite mutations. And so to sort of see how this works, say we have a population of agents playing this prisoner's dilemma, and we start with a population where everyone is a cooperator. So we've got 21 cooperators, no defectors, everyone is on average B minus C. That is, in every interaction, everyone's earning B minus C. And if we are going to say that cooperation is strategy 1 and defection is strategy 2, then this is situation, p equals 1, the whole population is playing strategy 1, and that's an equilibrium because there's no variation. And so any offspring is always going to be cooperation, or if you think about it from an imitation learning dynamic perspective, anybody that picks anybody else to copy is always going to pick a cooperator to copy, so everything is going to stay the way it is. But now the question is, what happens if a mutation occurs and changes this guy to a defector? Now we've got 20 cooperators and 1 defector, and the cooperators, they're going to always pay the cost, but they're only going to get the benefit back 19 out of 20 times, because the 1 out of 20 times that they get matched with the defector, they're going to get no benefit. And the defector, he never pays any cost, and every time he meets anyone, they cooperate with him. So he gets payoff B. And that means the defector's payoff is going to be higher than the cooperator's payoff, and that means that the mutant is doing better than the resident, which means that this equilibrium, the equilibrium of all cooperators, is not stable, because when some kind of update happens where you pick one guy randomly to change strategy, and then she picks cognitival proportional to payoff, you're most likely to pick this defector because the defector is doing better than the cooperators. So then defection will, you recalculate it, defection still is doing better, and so defection winds up spreading through the whole population. Okay, so that all cooperator situation was not stable, but now we're back in another situation where, again, there's no variation. The whole population is made up of defectors. And so the question is now, is this equilibrium stable? And so we can ask the same question, which is imagine that a mutation changed this defector to a cooperator. Now he's going to pay minus C and never get any benefit back. And the defectors are, have a 1 in 20 chance of getting matched with this guy and getting payoff B. And so this payoff, the payoff of the defectors, is better than the payoff of the cooperator, which means that cooperator will then die out and be replaced back with the defector. And so that means that this equilibrium of all defection is stable because the new mutant wouldn't do better, which is, again, the same thing from looking at the payoff matrix as saying that mutual defection is a Nash equilibrium. And you can sort of see that by thinking, like, what is this calculation? You're saying in a world where all of the other people are playing defect, so you know for sure the other person is going to play defect. The resident, that is everyone else in the population, is in this defect cell. If you switch to the cooperate cell, are you doing better or worse? You're doing worse, so it's an equilibrium, so a mutant would not get a foothold. Okay. And so given that, in a world where there's 2 possible strategies, you can represent the state of the population as a line where on this end you have entirely strategy 2, so P equals 0. On this end you have entirely strategy 1, so P equals 1. And, you can have in here where there's half the population is strategy 1 and half strategy 2, P equals 0.5, and just anywhere in between. Any point on this line shows what fraction of the population is strategy 1 versus strategy 2. And for this sort of setup where there's just 2 strategies, there's only 3 possible outcomes. So one outcome is everywhere along this line, the payoff of strategy 1 is better than the payoff of strategy 2. And so that means no matter where you start, you're always going to wind up at strategy 1. It means strategy 1 is an equilibrium, is a Nash equilibrium, and it's the unique Nash equilibrium. So whatever happens, you're going to wind up there, and you can see that in a payoff matrix sense. What this is going to mean is that if the fact that at strategy, like when you're right at strategy 1 is doing better than strategy 2. So that means when the other person's playing strategy 1 does better than strategy 2. So W should be greater than Y. And also down here, when basically everybody's playing strategy 2, strategy 1 still does better than strategy 2. So when the other person's playing strategy 2, strategy 1 still does better than strategy 2, so X should be greater than Z. That also means if you just take the consequences of that, that means that S1 is the only Nash, and this is what in evolutionary game theory we're called dominance. So strategy 1 dominates strategy 2 because no matter what is happening, it's always doing better. And again, here, strategy 2 is an equilibrium of sorts because if you're at p equals 0, where everyone in the population is strategy 2, it'll stay there. But the second any of strategy 1 is introduced by mutation, natural selection will drive the whole population down to this end where everyone plays strategy 1. Okay, so that's one possibility. Then another possibility is that when you're down at the end where it's mostly strategy 2, the payoff of strategy 1 is greater than the payoff of strategy 2, so selection tends to move away from strategy 2, which is the same thing we saw in the dominance. But on the other end, the opposite is true. That now when it's mostly strategy 1, the payoff of strategy 2 is higher than the payoff of strategy 1. So if you were to step off the end of all strategy 1, selection would drive you in the other direction. And so by continuity, there has to be some point in the middle where the two payoffs are equal. Because over here, strategy 1 is doing better, over here, strategy 2 is doing better. That had to switch somewhere. And the point at which it switches has to be a case where the two payoffs are the same. And so this is an internal equilibrium. And if we think about what this means in a context of a payoff matrix, given that strategy 1, so when you know for sure that the other person's playing strategy, well, so I do this one. If we know for sure that the other person's playing strategy 1, strategy 2 does better, so that means y should be greater than w. And when you're down here, so you know for sure the other guy's playing strategy 2, strategy 1 should be doing better than strategy 2, which means x should be greater than z. This, when you do that, you see that the only two equilibria are these. So this is an anti-coordination game. There's no symmetric Nash. That is, there's no Nash where both people play the same strategy. A side note is that, and we're not really going to talk about this, but there is actually a symmetric Nash in this game, which is called a mixed Nash. So if you have a strategy that says, rather than my strategy being type 1 or type 2, you can have a probabilistic strategy that says I play strategy 1 with some probability and strategy 2 with 1 minus that probability. And so you can have an equilibrium where everyone in the population, or it can be an actual equilibrium for everyone to say I cooperate with probability P, and if you know that the other person is going to cooperate with probability P, you can't improve your payoff by cooperating more or less frequently than that. And so it's symmetric in the sense that both people have the same strategy. It's just that it's a probabilistic strategy instead of a for sure do one or the other strategy. And so that's the sort of autonomous individual decision-making version. But when you think about this in terms of what happens in the population dynamics, what you get is what we'll call coexistence. That is, you get stable coexistence of the two different types. When you're at this point, some agents are playing strategy 1, some agents are playing strategy 2, and that's a nice stable equilibrium. And so in situations where neither S1 nor S2 are both equilibria, that is when neither of them are equilibria, you expect to get this coexistence. Okay, now the third possibility is kind of the opposite, which is when strategy 1 is common, strategy 1 does better than strategy 2, and when strategy 2 is common, strategy 2 does better than strategy 1. So out here, selection is driving you towards strategy 2. Over here, selection is driving you towards strategy 1. Again, and so that means that both of them are going to be evolutionarily stable. And again, by continuity, there must be some point in the middle where the two payoffs are equal. But now, when you're at this internal equilibrium, if a mutation arises that pushes the population a hair in this direction, now selection is going to carry it all the way down here to totally strategy 2. Or if a mutation occurs that pushes it a hair in this direction, selection will take it all the way down to strategy 1. And so what that means is this interior equilibrium is not stable, because the minute you step off of it, you go all the way one direction or the other. And so if we think about what this means in terms of the payoff matrix, well, when strategy 1 is common, strategy 1 is doing better than strategy 2, so W should be greater than Y. And then when strategy 2 is, when you know the other person's playing strategy 2 does better, which means that Z should be greater than X.
And so that means that both S1, S1 and S2, S2 are both equilibria. And so this we call bistability. And that's because there's two different stable outcomes. It can be 100% of one or 100% of the other. Either way, it's going to be stable. And so just to put these three things together, we've got three different outcomes. We have dominance, coexistence, and bistability. And then this maps onto the different types of games that we've been talking about, where in a social dilemma, defection dominates cooperation. In anti-coordination games like the Snowdrift, neither one is in equilibrium, and so you get some kind of mixed equilibrium. And in coordination games, both things are stable, and so you expect to see one or the other. You just don't know which one necessarily unless you know where the population starts. And then there's also this fourth kind of game that I mentioned briefly, the boring mutualism, where here cooperation dominates defection. So these are the four possible things that can happen in a two-player, two-option cooperation game. And in three of these four cases, it's very clear what we predict happens. Here it's definitely defection, here it's definitely cooperation, here it's definitely a mix. But in the bistability case of the coordination game, we don't know which one to expect. And so this we talked a little bit about a few lectures ago in terms of the concept of risk dominance, which I presented as this is this thing that economists do. But now we'll sort of see the evolutionary logic behind the risk dominance condition, which is, imagine that you have a coordination game set up like this. The question is, which equilibrium would you expect to be favored by selection? Which equilibrium would you expect to observe? Well, it depends on where the population starts. For example, if the population starts here, then selection is going to push the population to strategy 1. If the population starts here, selection is going to push the population to strategy 2. And so you can have the terminology that everywhere but from here to here is the basin of attraction for strategy 1, because anywhere in here, you're going to wind up getting pushed to strategy 1. This is the basin of attraction for strategy 2. Anywhere in here is going to wind up at strategy 2. And so the question of which strategy do you expect to be favored by selection is part of the answer to that is the bigger the strategy with the bigger basin of attraction is more robust in the sense that it is more likely to wind up being favored because, if you don't know where you're going to start, then it's more likely that you're going to wind up in the basin of attraction for the equilibrium that has the bigger basin of attraction. Therefore, you're more likely going to wind up having selection push you to the equilibrium that has the larger basin of attraction. And so the question of which equilibrium should you expect in a coordination game to be favored by selection is the same question as which one has the bigger basin of attraction. And so in this example, strategy 1 has the bigger basin of attraction because, if this is 0.5, this is 50-50, this sort of interior equilibrium is on the other side, and so there's a bigger chunk of the line that winds you up at strategy 1 compared to strategy 2. Here's an opposite example where strategy 2 has a bigger basin of attraction than strategy 1, and in almost all cases, one or the other is going to have a bigger basin of attraction, but there's this special case, this sort of non-generic case where when the unstable equilibrium is exactly at p equals 0.5, then the two strategies have exactly the same size basin of attraction and are exactly equally likely to attract things. And so if you want a shorthand for which strategy has the bigger basin of attraction, well, I guess first I should say, if you want to know, you can also just directly calculate the size of the basin of attraction for each of the two equilibria by saying, where is this interior point? That is, you can solve an equation that says, what is the value of P that leads the two strategies to have the same payoff? And that will tell you where exactly that is. And you can say, well, okay, is it below 0.5 or above 0.5? And that will tell you. But if you just want a shorthand for which one has the bigger basin of attraction, the answer to that is going to be the strategy that is doing better at the 50-50 makeup of the population. because if strategy 1 is the bigger basin of attraction, then this interior equilibrium is going to be on the other side of 0.5, and so at 0.5 strategy 1 is doing better, strategy 2 is bigger, the opposite.
And so that is exactly the risk dominance calculation that we talked about from before, which is when you don't know what the other person is going to do, just assume it's 50-50. And so say, if you're assuming that it's equally likely that you're going to play the two different strategies, which strategy would you do better to play? And that's the same thing as saying which strategy has the bigger basin of attraction in this evolutionary dynamic framework. And so this is the sort of connection between risk dominance and evolution. And as we talked about before, risk dominance is saying, I guess both of them. Again, it's the idea that the other person is going to play 50-50 with two strategies. That means that strategy 1 is going to risk dominate strategy 2 if, so when the two things are equally common, the expected payoff of strategy 1 is, they get W when the other guy has strategy 1, X when the other guy has strategy 2, and so if those two things are equally likely, it's just the average. So it's, W plus X over 2, and strategy 2's payoff is going to be Y plus Z over 2. So if W plus X over 2 is greater than Y plus Z over 2, S1 is risk dominant. And because the dividing by 2 is getting done on both sides, it's kind of redundant, it cancels out. We can, for simplicity, just sort of ignore it and say, if you sum across the row for strategy 1 and you sum across the row for strategy 2, who's doing better? And if you think about what the calculation that underlies the question of when the population is at 0.5, which payoff is higher, that is, so the expected payoff of strategy 1 for any given makeup of the population is with probability P, you play against strategy 1 and get W. With probability 1 minus P, you play against strategy 2 and get X. And for strategy 2, it's with probability P, you play against strategy 1 and get Y. With probability 1 minus P, you play against strategy 2 and get Z. And so if you substitute in, so then the condition for strategy 1 to be beating strategy 2 is that this thing should be greater than this thing. And if you substitute in 0.5 for P, that gives you back exactly the same condition as saying, imagine that you played one of the other two at random. And so one note is that the way economists have talked about risk dominance is just, if you've got two equilibria, the risk dominant one should win. Fine. But a key element of evolution is randomness and embracing the fact that things are not just like totally perfectly deterministic. It's not the case that the higher strategy always wins, or in this case that the strategy with the bigger basin of attraction always wins. But it's just like the bigger the basin of attraction of one relative to the other, the bigger the fraction of initial starting points that lead you there, the more likely it is to occur. And so really, you should think about this as a continuous concept, which is the more W plus X exceeds Y plus Z, the more likely it is that you're going to wind up in strategy 1. So... So if this is our risk dominance condition, there's like a real fundamental difference between this condition and the Nash condition. So if you want to say what's the condition for strategy 1 to be Nash, it's just that W has to be greater than Y. And but when you think about risk dominance, you have X and Z also appearing in there, which is to say it doesn't matter just how you do against yourself and someone else does against yourself. You're not just thinking about unilateral deviations anymore. And now you have to think about what happens when you have to actually play members of the other, people with the other strategy. And so what that means is, even in cases where W is greater than Y, if Z is a lot bigger than X, that is, if X is very negative and Z is very large, you can still wind up with the other equilibrium winning. And so one of the implications of that, which we sort of saw demonstrated in the games that you guys played in class,
is that if you hold x and y constant, then it's the case that the strategy with the bigger payoff against itself is going to do better. So, if you hold x and y constant and you just say w plus x has to be greater than y plus z for strategy 1 to be risk dominant, if x and y are held constant, if you increase w, that's going to make strategy 1 more likely to be selected. If you increase z, that makes strategy 1 less likely to be selected. So all else being equal, selection will tend to favor the equilibrium that's more efficient. That is, that generates the higher payoff for both players. But it needn't be the case that that is necessarily going to happen. So here, just as an illustrative example, when here x and y are just fixed at 1, it kind of makes sense that if the payoff of being in this equilibrium is slightly bigger than this one, this guy will be favored some. But if it's massively bigger, it's much more likely that you're going to wind up in strategy 1. But what risk dominance shows you is that that's not enough to really understand what's going on, because even if it's the case that w is greater than z, you can still have strategy 2 winning if x is much smaller than y. And so it means that the efficient equilibrium need not be the risk dominant equilibrium, and this creates a different kind of social dilemma where it's not necessarily, that is, the social dilemma in the prisoner's dilemma is, well, one's, the inefficient strategy just is dominant, is totally dominant over the efficient strategy. And here, it's not dominance in that sense, but in the sense it's this risk dominance, which is, they're both equilibria, but one of them is, is safer in a certain sense. And so, for example, if we change the off-diagonal payoffs so that now x is very negative, then even though strategy 1 is way more efficient than strategy 2, still people will wind up learning to play, or evolution will wind up favoring the less efficient equilibrium. And this is the thing that we saw happen in your game, where there was the off-diagonal payoff of -20 if you cooperated and the other person defected. You guys learned to play the less efficient defecting equilibrium because you didn't want to risk getting burned. Okay, so just to summarize this, we can have a few different scenarios. In one case, S1 is the only Nash, and there the expected evolutionary outcome is everyone plays S1. Or if S2 is the only Nash, then the expected outcome is everybody plays S2. When neither S1 nor S2 are Nash, so it's an anti-coordination situation, then you get an interior equilibrium at some value of P, and specifically it's the value of P at which the expected payoff of the two strategies is equal. And then when both of them, S1 and S2 are both Nash, so it's a coordination game, and S1 risk dominates S2, then we expect it's more likely that it will wind up at P1, although it might wind up at P equals 0 if you start very close to P equals 0. And then the opposite is true if they're both symmetric Nash, so it's also a coordination game, but now S2 is risk dominant over S1, then you expect P equals 0. And so this is the kind of complete characterization of the sort of expected outcomes in a game of this nature where there's two players with two options. And so one sidebar is what we've talked about so far today is which direction evolution will push you in any given situation, but we didn't talk about the speed with which evolution would happen. And so, the idea being the higher, so we said the strategy with the higher payoff becomes more common, but the bigger the difference in payoffs, the more quickly the population is going to move in the direction of the higher payoff strategy. And so one way to formalize this is with the replicator equation. And so this is I say a sidebar because it's like, if you don't know differential equations, don't worry about it. It's not going to be on the test, but this is just for people that know differential equations and are interested in this. I would be remiss to give a lecture on evolutionary game theory and not show the replicator equation. So the idea is, again, these are just the payoffs of the two strategies, right, are the fraction, well, whatever, we did this before, right? So P is the fraction of strategy 1. So with a W, X, Y, Z payoff matrix, these are the expected payoffs of the two strategies. And so what the replicator equation says
is that the change in p over time, so dp dt, is going to be the amount of strategy 1 that is currently there times the payoff of strategy 1 minus the average payoff in the population. So p times payoff of strategy 1 plus 1 minus p times the payoff of strategy 2 is the average payoff. And so this is saying that if your payoff, if strategy 1's payoff is higher than the average, this is going to be positive and it's going to tend to increase. If it's less than average, it's going to be negative and it's going to decrease. And the better it's doing relative to the average, the faster that change is going to be. And in this particular case of only 2 strategies, you can refactor this to look like that, which is saying that you have this p times 1 minus p it's sort of like a classic growth thing that it's saying whatever, it keeps it bounded on the interval 0 to 1. But the key point here is that the sort of rate of change is going to be a function of the difference in the magnitude between the 2 payoffs. So this is our introduction to evolutionary game theory, and at this point, we've sort of concluded the key tools, these sort of analytic tools we need for understanding things. We've got Nash equilibrium, we've got risk dominance, and we've got the basic idea of evolutionary game theory, and we've got our sort of different types of games. And what we're going to start doing now for the rest of for the next section of the class is using these tools to understand all of these different mechanisms for the evolution of cooperation, and it's roughly going to be 2 lectures for each mechanism. And the mechanism that we're going to do next is reciprocity, the shadow of the future, as they call it, which is to say, when 2 agents interact repeatedly, then your action today has some consequence in the future, and the shadow of the future, sort of projecting back into your current decision, can influence your decision making. But basically what we're going to see is how most of these mechanisms for the evolution of cooperation translate into changes in the payoff structure of the game that change it from one type of game to another, and in general change it from the social dilemma of the prisoner's dilemma into some other type of game, such that you can have cooperation being selected and or are changing the relative risk dominance of different strategies so you can get cooperation actually winning. So have a good weekend. Oh, important note, there's no class on Tuesday. So our next class is Thursday. Have fun on Tuesday at 11:35, and I'll see you next Thursday.